When we combine solutions of lead nitrate and potassium iodide, a colorful material appears. This is actually a solid called lead-2 iodide.
Chemists can actually predict what products will be for a reaction, knowing some general patterns of reactivity. And one very general kind of pattern of reactivity you'll see in this class is what's called an exchange reaction. And so in that little diagram on the left, AX represents a positive and a negative compound, a cation and an anion. So maybe it would be NaCl. The Na would be the A, the positive part. Chloride would be X, the negative part. And then By would also be ionic. Maybe it would be something like silver nitrate, all right? The silver plus would be B, and the Y would be nitrate. And what happens is the anions exchange partners, if you will. So the silver starts dancing with the chloride, and the sodium starts dancing with the nitrate. So on the other side, you have essentially cation-anion swap. Sodium and nitrate would come together, or silver and chloride. That's what an exchange reaction is, and exchange reactions are sometimes called double displacement, same thing. Now in this example that we just saw the little video for, you have lead-2 nitrate and potassium iodide, and I just underlined the cations, the metals, the positive parts. And you can think about them as trading places, or you can think about the anions, doesn't matter. But potassium is going to start dancing with iodide to make PbI2, and potassium is going to start dancing or trading partners to start dancing with nitrate to make KNO3. Now notice that lead was positive 2 on the reactant side. Lead is going to be positive 2 on the product side. So that's why we need 2 iodides, PbI2, and not just PbI. We don't change the charges in these exchange reactions. And that's also why, even though there were 2 nitrates needed for lead, we're going to write it as KNO3, 1 nitrate per 1 potassium, because potassium's positive 1, nitrate's negative 1. So when you balance it, you need 2 Ki's and 2 KNO3s to essentially make the lead happy. But anyway, this is really cool. And PbI2 now, we know that's an iodide. Usually iodide is AQ, i.e. with potassium. But when iodide is with mercury 2,2 plus, silver plus, and lead 2 plus, it makes a precipitate. So that's why PbI2 is a solid right there. That's going to be the action of the reaction if you wanted to figure out the net ionic reaction, stuff like that. This kind of reaction is called a precipitation reaction, which is what we've kind of seen before and what we'll talk about more here again. So anyway, if you hear about these exchange or double displacement reactions, you just want to figure out what the new products will be by flipping cations and anions. Cation on the first one will start dancing with the anion on the second one, and vice versa.
In the test tube, we have an aqueous solution containing iron 3 ions. To this, we will add a solution of sodium hydroxide. A precipitation reaction occurs that produces iron hydroxide, an insoluble metal compound.
Precipitation reactions are cool. You can usually see the solid that forms, which is pretty great. In this case, we're making iron 3 hydroxide, which is very insoluble. Hydroxides are usually insoluble unless they're with ammonium or sodium, potassium, lithium, the group 1A cations. So that's kind of a cool thing to know. Anyway, this is another exchange reaction. The iron is the cation, the sodium is the cation there, and they're going to flip places. So iron's going to start dancing with hydroxide, and sodium's going to dance with nitrate. Now iron is positive 3 on the left, on the reactant side. It needs to be positive 3 on the product side. So hydroxide is a negative 1 ion. You're going to need 3 of those to balance the positive 3 on the iron. So when you balance this all out, you need 3 NaOH. You're going to make 3ANO3, stuff like that. The net ionic equation here is going to be basically just forming the solid. Remember, in net ionic reactions, you always show the solids, liquids, and gases. Don't break them up. And anything that goes into making those is going to be reactants. So in this case, it would be iron 3 plus and 3 hydroxides making FeOH3. That also means then that the sodium ion and the nitrate ion are spectators. They don't really do anything. Now, eventually we're going to start talking about why reactions happen. We're going to talk about the driving forces that make chemicals happen, that make chemicals form. And actually making it precipitate is a pretty strong driving force. It's a reason why reactions want to happen. We will come back to this in a future lecture, but I want you to hear these terms in case we start talking about it sooner.
The reaction of hydrochloric acid and sodium hydroxide is an acid-base reaction. A color-changing indicator allows us to see that a reaction occurs.
Acid and base reactions give a lot of energy to a lot of different chemical processes, as we'll see as we go forward in this class. All acid and base reactions at their core, they end up making water, and they end up making what's called a salt. And a salt is basically the other leftover of acid and base reactions. So for this one, it's sodium and chloride coming together to make sodium chloride. That's the same as table salt. But a salt doesn't have to be table salt. For example, if you had potassium hydroxide and hydrobromic acid, you would end up with KBr, potassium bromide. That would be another kind of salt. So a salt is the product of an acid-base reaction. But the important part for us is that actually just making water is the driving force. That's why this reaction happens. Now in that little video, it shows the solution turning purple, and you can make that happen. If you add a compound called phenolphthalein, it'll turn your solution kind of a pink color once the acid and base react. However, most of the time, acid and base reactions colorless. All right, so you don't see anything, you don't see solids form, you can't tell if water has formed. Sometimes you can feel heat though. These reactions give off a lot of energy when they happen, so sometimes they'll feel kind of warm. But just kind of FYI, it may look like nothing happened, but maybe something did happen. The net ionic reaction, when you have an acid and a base comes together, is almost always hydroxide plus H plus making water. So making water is important. A lot of energy is created. This net ionic equation applies to all reactions of strong acids and strong bases. We'll talk about those in just a second. Sometimes acid-base reactions are called neutralizations. When the acid and base amounts are equal, you will create water and a salt. If it's sodium hydroxide and hydrochloric acid, the salt is sodium chloride. So in theory, you could have a strong acid and a strong base react, and you could drink the resulting water because it would be like salt water. But nobody's going to try that on my watch. I don't trust anything that's been measured that much, and your life is more important to me than some silly chemistry demo. But in theory, if you do the neutralization reaction right, you should be able to drink the result, but don't try it.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution.
Acids are really important to chemists. Acids always have a hydrogen listed first, and there's a lot of energy involved when you use an acid. Now, acids and bases react to make water. Anytime you can make water, you've got a lot of strong energy given off. Hydrochloric acid is a strong acid, and when you put it in water, it really doesn't stay as HCl at all. It breaks up 100% to H plus and Cl minus. So hydronium is H3O plus technically. And that's officially, in the chemistry world, what acids create. But a lot of times hydronium is just listed as H+. Now here's a list that I really want you to tune into. There are 5 strong acids, and these are really important for stuff we're going to talk about. Hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, HNO3 is nitric acid, HClO4 is perchloric acid. And knowing those 5 strong acids is going to have lots and lots of uses. All of those acids break up 100% to an H plus ion and some kind of counter ion. So chloride if it's HCl, bromide if it's HBr, stuff like that. Make sure you make a note of that.
Hydrofluoric acid is a weak acid because it only partially ionizes. At any one moment, most of the HF molecules have not split into their ions.
So there are 5 strong acids, which we talked about on the last page, but there are thousands upon thousands of weak acids. And weak acids just don't break up to the same extent that the strong acids do. So in the video right there, it showed hydrofluoric acid, HF, and maybe one of every 1,000, every 10,000, every 100,000, who knows, molecules do break up into H+, and in this case, F-. But most of them stay the same. So you don't have the power of in a weak acid that you do of a strong acid. You don't have as much H+ to deliver. Most acids are this way, and there's some examples of other weak acids, but again, there's thousands of them. Acetic acid is the active ingredient in vinegar, so it's pretty common. Carbonic acid is something that actually makes drinking water a little bit acidic. It's totally normal, don't worry. Phosphoric acid, etc., etc. Most of the foods we eat and most of the things we drink are actually weak acids. So again, if you know those 5 strong acids, you can just assume that all other acids are going to be weak. Most of the acids will have an H listed first, but you can see there that acetic acid is the one notable exception where the H is listed last. It has to do with the formula, which you can see in the upper right-hand corner, that CH3COOH part. It's only the last H which is acidic. If you take the H+ off, you have the acetate ion, which is one of the polyatomic ions. So that's why I guess they list it that way. I don't know. As a science teacher, I would so prefer it was listed H, CH3CO2, but, you know, nobody listens to me, alas.
NaOH, sodium hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
Acids are strong. Bases are strong as well, but for different reasons. So what is a base? A base is a metal hydroxide. You have to have a metal, and it's next to the polyatomic ion hydroxide, which is OH-. So just like with acids, there are strong bases and weak bases. There are 3 strong bases you really need to know / memorize. Sodium hydroxide, potassium hydroxide, lithium hydroxide. Those dissociate 100% into the metal ion and hydroxide. So NaOH goes to just Na plus and OH-. Same thing for lithium and potassium hydroxide. They will break up into K+ and OH-, for example. Very powerful. Lots and lots of energy. And you want to be careful with these. They are just as strong and deadly, if you will, as the strong acids are.
On the left is H2O, water. On the right is NH3, ammonia. The dots and lines represent electrons. Ammonia acts as a base in water. It removes a hydrogen ion from water to create hydroxide and ammonium ions. In solutions, only a few hydroxide ions are created at any one time, so ammonia is a weak base.
Just like we saw with acids, there are strong acids that dissociate 100% to H+ and the counterion, while weak acids, maybe 1 in 10,000 break up. Well, there's also strong bases like we saw and weak bases, and all of these things create hydroxide through one version or another, but the weak bases just don't give as much. So while the strong bases, you can see the hydroxides right in there, a lot of times the weak bases don't have hydroxide listed. So the great example is ammonia, NH3, which is a real common weak base. Now, NH3 does not have any hydroxide, but what happens is ammonia reacts with water, like the video in the upper right-hand corner says, and makes ammonium, which is NH4+, and ammonium is different than ammonia, FYI. But anyway, ammonium and hydroxide. So that's where the hydroxide comes from, and that's why it's a base. So those examples right there are all bases. Most of the negative polyatomic ions are bases: carbonate, phosphate, sulfate, those kind of things. Hydrazine is another type of base. So notice that it's basically either a nitrogen-containing compound or a negative polyatomic ion. But here's the punchline. If you know that you have a base and it's not one of the 3 strong bases, you can assume it's weak. There are thousands upon thousands of weak bases, but only a couple of strong bases. So that's what's important. And again, strong bases give 100% hydroxide. All of these weak bases would not give the same thing. A lot of our household cleaners are weak bases. So if you've cleaned your house before, you're probably using a weak base. This is a list showing the some strong acids and the strong bases, or at least a lot of them. You can see the strong acids in the upper left-hand corner and the strong bases in the upper right-hand corner. Now again, there's just thousands upon thousands of both weak acids and weak bases. And again, most of the time, if you hear about an acid, you can assume it's weak. And if you hear about a base, you can assume it's weak unless you know it's one of the strong ones. I might once in a while share a different strong acid or strong base, but I would tell you if it was, okay? And again, most of these are weak, so you don't see the same. But again, things like aspirin and vinegars, acetic acid, stuff like that. There's a lot of acids around us and a lot of bases, so these are important for us in life as well as in chemistry. Here's a question you might see. It says, which of the compounds below is not an acid in water aqueous solution? Okay, well, anything that has an H listed first is going to be an acid. So you can see that B, which is phosphoric acid, D, hydrochloric acid, and E, which is hypoiodous acid, a more rare acid, but they all have H listed first. Those are going to be acids. So it's going to come down to A or C. A is the most common weak acid. It's acetic acid. The hydrogen's listed at the end. I don't know why, but that's just the way it is. You kind of got to know that. So acetic acid is an acid. And C is probably the most common weak base, which is ammonia. So ammonia is a weak base. It has hydrogen, but it's not an acid. It's going to be a base. When it reacts with water, it makes the ammonium cation and hydroxide. That's where the base part comes in. We talked about precipitation reactions. Let's talk about some other types of reactions now too. Oh, we also talked about acid-base reactions as well. A gas-forming reaction is an exchange reaction, double displacement, and one of the products is going to be a gas. So calcium carbonate there is reacting with hydrochloric acid to make calcium chloride and what's called carbonic acid, H2CO3. Now it doesn't look like there's any gases there, which is true. But what happens in a gas-forming reaction is that one of the products is usually unstable and it further breaks down into the gas. And in this case, that's carbonic acid. If you see carbonic acid, H2CO3, just realize that H2CO3 is going to break down into CO2, a gas, and water. So really this reaction should be listed as calcium carbonate plus 2 hydrochloric acids makes calcium chloride plus CO2 gas plus H2O liquid. So gas-forming reactions will form a gas, but it may not be readily available. So I would definitely know that the carbonic acid is going to break down to CO2 and water. If you see carbonic acid as a product, you know it's going to be a gas-forming reaction. Ammonium hydroxide is another common example of a gas-forming reaction. Ammonium hydroxide will also break down into a gas, ammonia, and water. So if you see ammonium hydroxide as a product, you should also know that it's going to break down into NH3 and CO2. They're both gases. They don't look like gases. They'll look like they're AQ things because they are, but they'll further break down into gas products. We'll see this in the lab. We're going to do the net ionic reactions lab.
When calcium carbonate, marble, is placed in hydrochloric acid, carbonic acid is produced, which is converted to gaseous carbon dioxide and water in a gas-forming reaction.
Here's a question you might see. It says, which equation below best represents the balanced net ionic equation for the reaction of magnesium carbonate with nitric acid? Okay, so notice it's net ionic equation. We don't want any spectators, okay? So magnesium carbonate has a carbonate, and most of the negative polyatomics, when they react with anything but group 1A and ammonium, will make insoluble compounds. So notice that MgCO3 is listed as a solid, and that's correct. Carbonates usually are insoluble unless they're with sodium, potassium, and lithium. It's going to react anyway with magnesium, thanks for playing. It's going to react with nitric acid, which is HNO3. And this is going to be a displacement reaction. So the H plus and the Mg plus are going to trade places. You're going to make magnesium nitrate on the other side. And what looks like initially H2CO3 is actually going to be CO2 gas and H2O liquid. This is a gas-forming reaction. Remember that H2CO3 will break up into H2O, which is the product there, and CO2. So it's kind of a thing you just got to pay attention to. Well, anyway, answer A is the balanced molecular reaction. It shows all the cations and the anions, but we don't want the balanced reaction. We want the net ionic reaction. So if you look at just the aqueous species, HNO3 on the left and magnesium nitrate on the right, both of those have nitrate. Nitrate is a spectator ion, and you want to pull them out. So if you pull out the NO3s, keep the gases, liquids, and solids, you can see that HNO3 goes to H+, and magnesium nitrate goes to just magnesium 2+. So answer B here is actually the net ionic reaction. It does not include nitrate because nitrate is a spectator. Good to go. A combustion reaction is another kind of reaction that's used a lot, especially in organic chemistry. And in a combustion reaction, the easiest way to think about it is you have something organic, which usually has carbon and hydrogen, sometimes oxygen, sometimes even nitrogen. And you're going to burn it in O2 because oxygen's a gas, and the products will always be water and CO2. If you happen to have nitrogen, then you'll make NO2. That's the one exception to it. So this is actually very common, and it's used, for example, in our cars. If you have a gasoline engine in your car, then it's using gasoline, which is essentially a carbon-hydrogen compound. It reacts with the oxygen to make CO2 and water. But anyway, these are just some examples. Here's C2H4 reacting with oxygen to make waters and CO2s. The next problem down there, it's a nitrobenzene compound. You don't need to worry about that name, but it also burns an oxygen to make water, CO2, and because nitrogen is there, you're going to make some nitrogen dioxide. So combustion reactions are usually they give off a lot of energy. They're very exothermic. They're kind of fun because you get to burn things. But anyway, that's kind of the idea of what's going on.
The purple solution is aqueous potassium permanganate. The colorless solution contains iron 2+ ions. When we combine them, a redox reaction occurs. The permanganate ion is reduced to manganese 2+, and the iron is oxidized to iron 3+ ion.
An oxidation reduction reaction is another powerful type of reaction that we use around us all the time. Redox reaction, which is the abbreviation for it, redox reactions are used in batteries, and we all use batteries for cell phones and all kinds of things. It's also used, though, in our bodies, like getting oxygen from the outside to inside is actually a type of a redox reaction. So anyway, in a redox reaction, you have electrons that are transferred from one reactant, which is called the reducing agents, to another reactant, which is called the oxidizing agents. And it's important to know where electrons come from and where they go to in a reaction, all right? And they're very common, they're very powerful, there's lots and lots of uses for it, and let's talk a little bit more about what a redox reaction is. At this point, I need to introduce my friend Leo the lion, and Leo says, "Grrr!" All right, sound effects not necessary. Leo the lion says GER, and Leo says GER is an acronym that will help you. Leo stands for lose electrons oxidized. GER stands for gain electrons reduced. So something that is oxidized has lost electrons. And you can see there that the zinc is losing 2 electrons to become zinc 2+. So notice that losing electrons means that electrons will be products. GER is gain electrons reduced. So the copper 2+ is gaining electrons to become copper metal. Reduced means electrons will be reactants. All right? So oxidized and reduced are real common. Unfortunately, in the real world, a lot of times people use reducing agent and oxidizing agent instead of oxidized and reduced. Now, something that's a reducing agent is something that's been oxidized. So zinc has been oxidized. Zinc is the reducing agent. And something that's been reduced, like copper 2+, is oftentimes referred to as an oxidizing agent. So copper 2+ is the oxidizing agent. It's allowing the zinc to be oxidized. I guess that's the use for it, but chemists would call copper 2+ being reduced. I'm just the messenger. I apologize for the confusion. I have nothing to say about it. Anyway, if you don't like my Leo the Lion says Gara, which is fine, you can use oil rig. Oil means oxidation is losing, rig is reduction is gaining. Either way you want to do it is fine. But understand the terms oxidized and reduced, and know that the agents are the opposite. So reducing agent is something that's been oxidized, an oxidizing agent is something that's been reduced.
When a piece of copper metal is placed in a solution containing silver ions, solid silver crystallizes on the copper. While the silver crystals grow, copper ions are also released into solution, giving the solution a blue color.
This is a cool reaction. You can take a strip of copper metal and put it in some silver ions, and after a while you begin to see that kind of mossy stuff grow on the copper. Believe it or not, that mossy stuff is silver metal. It's kind of unpurified silver metal, but it is silver metal. And a blue color pops in. Blue is often the color that's associated with a copper 2+ ion. So this is an example of a redox reaction. And if you have a redox reaction, something has oxidized and something is reduced at the same time. You can't have just one part being oxidized and one being reduced. They have to be done at the same time. Oxidized species become more positive. So copper going to copper 2+ means that the copper metal, copper as a solid, has lost 2 electrons. It becomes copper 2+. So copper has been oxidized. It's lost electrons. Reduced species gain electrons. They become more negative. So notice that silver went from a +1 to silver 0, which is what Ag solid is. So it became more negative because it gained electrons. And what we're doing here by looking at more positive, more negative, we're really using oxidation numbers, and they can help by figuring out what's been oxidized and what's been reduced. Here's a reaction. Iron metal, which is Fe solid, reacts with copper 2+ to make copper metal, Cus, plus iron 2+ Aq. And it says which of the following is correct. And we've got reduced, oxidized, blah, blah, blah. Okay, so first of all, notice that the last two answers are both reduced and or oxidized. And you have to have something oxidized and something reduced at the same time. You can't have 2 species reduced and 2 species oxidized. So C and D are out. Now, iron is going to iron +2. So iron on the left is losing 2 electrons. It's becoming more positive. We would say that iron is being oxidized. Copper 2+ is becoming more negative as it goes to copper. So going from 2+ to copper 0, which is what copper solid is, that's becoming more negative. It's going towards negative numbers. So copper 2+ is gaining electrons. Copper 2+ is being reduced. So answer B would be the best answer here. Here's the actual what's called a half reaction that shows the electrons. Remember, electrons are always negative. So +2 for the iron and 2 -1 electrons. That whole thing goes to 0, and that's what the iron is. And you can do the same thing on the copper side too. So oxidation numbers can be helpful. Oxidation numbers usually are just equal to the charge that you would experience on the ion, but there are some exceptions. So these are the official boring rules. If free elements are always 0 for the oxidation numbers. So if you have zinc solid, copper solid we saw on the last slide, O2 gas, bromine is a liquid, sodium metal, mercury is a liquid, helium gas, all going to be oxidation numbers of 0. And again, most of the time, the second one there, it says the most simple ions, the charge literally is the oxidation number. So chloride has a -1 charge. It'll have a -1 oxidation number. Magnesium 2+ would be +2. Aluminum 3+ would be +3, etc., etc. Now in compounds, polyatomic ions, stuff like that, fluoride, always -1, oxygen, usually -2, and hydrogen, usually +1. There are some exceptions for O and H, but usually that's the way it rolls. And the overall sum of the oxidation numbers is going to be 0 for a compound or equal the charge if it's an ion. And I'll show you some examples of how this works here in a little bit. So in this example in the upper right-hand corner, you have MnO2, manganese 4 oxide, reacting with aluminum to make manganese metal and 2 aluminum oxides. Well, the aluminum, which is by itself, and the manganese, those are both elemental versions, so they'll have oxidation numbers of 0. And on the MnO2 and the AlO2, you have oxygen, and oxygen is usually -2. So in MnO2, if oxygen's usually -2 and there's two of them, that's -4. And the manganese is going to have to balance out that -4 with its own +4 because MnO2 is neutral. So that's why the Mn is +4. And in aluminum oxide on the right, oxygen's usually -2 and there's three of them, so that's -6. The two aluminums have to balance it out. If each aluminum is +3, it'll balance it out, no problem. So that's a very fast way to look at oxidation numbers. It's mostly just about what the charges are in the species. For H2S, all right, if you wanted to figure out the oxidation numbers, well, hydrogen's usually +1, and there's two of them. So sulfur is the one that would be a little weird to figure out. So what you can do is that the overall molecule is neutral. So the overall molecule is not going to have a charge. And you know that there are two hydrogens, each at +1, and we just don't know what the one sulfur is. Let's call that X. So when you solve for this, 2 times 1 is 2, 2 plus 1x, or 2 plus x equals 0. Put the 2 on the other side, x comes out to be -2. So the sulfur here has an oxidation number of -2. And that kind of gels because sulfur is in group 6A. 6 minus 8, those are usually -2, and that's what we're seeing here for sulfur, so that doesn't seem too crazy. We can also do the same thing for sulfur in sulfite, all right? Now, sulfite is a polyatomic ion, but sulfur is going to have an oxidation number and all that. So what we do is we say that, well, oxygen's usually -2, like we said, and there's 3 of them, all right? So the 3 oxygens times the -2 charge plus whatever sulfur is, and there's 1 of them, so 1x. But while the last example, everything equaled 0, here everything equals -2 because this thing has a charge on it. So when you do the math for x, it's like -2 equals x minus 6. So you put the -6 on the other side, it becomes a +6. 6 minus 2, this sulfur is +4. So good old sulfite sulfur is +2, but notice that sulfur in the H2S was -2. So you can have a variety of numbers, especially when you get to the central atom of polyatomic ions. But this terminology, this format, will allow you to figure it out no problem. You can then see what's happening.
The atoms in hydrogen fluoride have oxidation numbers of +1 and -1 respectively. These are the charges the atoms would have if the bond were completely ionic. The oxidation numbers on the atoms of the perchlorate ion indicate the charges they would have if the transfer of electrons were complete. Such complete transfer, however, does not occur in reality.
So H and F, H is +1, F is -1, and that's not a big deal because those are the charges you would normally expect for those compounds. But when you get to something like perchlorate, ClO4-, and you want to figure out the oxidation number, it's usually the central atom which is going to be unusual. So oxygen's -2, and there's 4 of them, -8, but -8 plus the chlorine equals -1. So when you figure out what the chlorine here is going to be +7. Now, this isn't an actual ionic charge, but it is what the chlorine would be if you'd rip the oxygens out. Oxygen's more electronegative than chlorine, so it is going to pull electrons more its way. But this is useful then to figure out if you have an oxidation-reduction reaction or not. If you know the chlorine's +7, you can see if it's changed to something else, and you'll be good to go. Single replacement reactions are a type of reaction where you have like a piece by itself and it's changing places with the corresponding piece in a second species. Now I know that's about as clear as mud, so let's look at an example down there where copper in the first one is reacting with silver nitrate. And copper and silver are both metals, they're both positive cations, so they're going to trade places. And you end up making then copper 2 nitrate, because copper usually is +2 more often than not, and silver metal. So that's an example of a single replacement reaction. The copper and the silver trade places, but there's no corresponding anion with the copper, so it's only in this case like the metal that trades places. The second example is similar. Magnesium and hydrogen are both positive, so they're going to be the parts that swap. So magnesium starts dancing with chlorine, and hydrogen is by itself. Now hydrogen's a diatomic, have no fear of ice clear brew, so write it as H2. But anyway, the important part here is that all single replacement reactions are redox reactions, all right? I don't know of any exceptions to this. So if you know about single replacement, it can make the world a little bit easier. You know automatically it's redox. Now to confirm that it's redox, you can look at the oxidation numbers. Now real briefly here, I'll tell you what the oxidation numbers are. The elements by themselves are 0. So copper, magnesium, both 0. The silver and the hydrogen gas are also both 0. But it's the other pieces that aren't 0. So silver and silver nitrate is +1. The nitrogen, +5. Oxygen, -2. Those are the oxidation numbers. You can pause the video and work these out to make sure I'm right, by the way. Copper, +2. Nitrogen, +5. Oxygen, -2. On the bottom, let's finish this off. Hydrogen is +1, chlorine's -1. Magnesium chloride, magnesium's +2, chlorine's -1. Now, why I did that? Notice how copper went from a 0 to a +2. Copper had to lose electrons to become +2. So your copper metal goes from 0 to +2. It's been oxidized. But if something's oxidized, you have to have something reduced. Well, notice that silver went from +1 to 0 on the other side. So the silver was gaining the electrons. It was being reduced to make silver metal. And you can do the same thing on the bottom. Magnesium is being oxidized. It's going to +2. And the hydrogen H+ ion is being reduced. It's going to H2. These are the value of oxidation numbers. You can tell by a change in oxidation number that something's been oxidized or reduced. Now notice in the first example, nitrate, nitrogen's +5, oxygen's -2, and that doesn't change on the other side. Nitrogen's still +5, oxygen's -2. So nitrogen and oxygen were not oxidized or reduced. There's no change in the oxidation number. And the same thing for chloride in the second example. It's -1 in HCl, it's -1 in MgCl2. Chloride was not oxidized or reduced in that reaction. So it can be pretty cool in telling what's been oxidized and reduced.
Nitrogen monoxide is a colorless gas, which we can observe when we bubble it through water. When it contacts air, and therefore oxygen, an oxidation-reduction reaction quickly converts it to nitrogen dioxide, a visible brown gas. When heated iron comes in contact with gaseous chlorine, a reaction immediately takes place, forming a dark brown solid, iron 3 chloride. This oxidation-reduction reaction involves a transfer of electrons from atoms of iron metal to atoms of chlorine, a halogen.
Redox reactions can be pretty spectacular, and both of these are examples of them. You can see they're for nonmetals and nonmetals, metals and nonmetals, all different kind of capabilities and reaction types will happen when it comes to redox. And there's oftentimes a lot of energy given off, and they're pretty cool. The important thing about redox, once again, is that when you hear reducing agent, that means that things are oxidized. And if you hear about oxidizing agents, those are things that are being reduced. And in the real world, if you listen to podcasts and health things, they'll say, oh, well, this is a great reducer, this is a great oxidizer. They're usually referring to reducing agents and oxidizing agents, but it's not all the time. So it can get really confusing. And I have literally stopped people in presentations and said, do you mean oxidizing agent or oxidized? And they have to think a little bit. But anyway, you should do this too if you get to it, because it can be very confusing, and all scientists face this. The joys of being a scientist. Okay, so that's the end of Chapter 7, Part 1. I really appreciate you spending your time with me, and I hope this has been helpful. Now remember, Chapter 7, Part 1 is only over Sections 7.1 and 7.2. We'll look at the rest of Chapter 7 in Chemistry 222, but it's nothing you have to worry about right now. If you have any more questions on things, definitely reach out to me. I'm happy to help. There are some resources to help you study this material a little bit more. I really, again, once appreciate you being here. Hope this has been helpful. Have a great day.